Here we have section 894, rather, periodic trends in ionization energy. Our objectives: be able to define ionization energy and the trends that we see on the periodic table for ionization energy, and also predict the relative ionization energy of atoms using the periodic table. Okay, take a look at this chart to the right, and the first thing I want you to do, to the right of your notes, I want you to write the trend that you see as you go across periods. You'll see periods. These are the periods. So what's the trend as you go from lithium to neon? What's the trend as you go from sodium to argon? I want you to write the trend that you see to the right of your notes. And then while you're doing that, or when you come back here, we're going to talk about ionization energy, which is the energy required to remove the most loosely held electron. So we're talking about taking an electron away from an atom. That's what we're talking about when we're talking about ionization energy. How much energy does it take to steal an electron? So the higher the value, the higher the ionization energy, the harder it is. So it's really hard to take electrons away from these, and you'll notice those are the noble gases. Kind of small print, but those are the noble gases. Really hard to take it away from there. Pretty easy to take it away from those, those down there. Most of those are the group 1A alkali metals. Now there is more than just what they call the first ionization energy. There's also the second. That would be if we wanted to take away the second electron. Some atoms, readily lose more than one electron. So you can always try and take away more than one, and you can get it from any one of them. Just some of them takes a lot more energy. But the first ionization energy is taking away the first one. Second ionization energy would be taking away the second one. Third ionization energy taking away the third one, and so on. And the second ionization energy is always higher than the first. So let's talk about some trends that we see, and hopefully you wrote down, and you already know a little bit of this, but trends as we move from left to right across the periodic table. And you can see here we've got our elements in group 2, or period 2 rather, and as we go across the periodic table, you can see in general, if you can see these, it goes 520, 899, 801, 1086, 1400, 1314, 1680. In general, it's not perfect, of course, but in general it's getting bigger as we're going down this list, and going down that list is actually going across from left to right on the periodic table. So ionization energy increases as you go from left to right. So the upper right hand corner is higher for ionization energy than the lower, or the left. And the reason is, as atoms become smaller, it is easier for them to hold those electrons in. So the ones, a lot of this is dependent on size. In fact, the majority of this all depends on size. And, the ones like fluorine. Fluorine is the smallest of these listed here. So that atom is really small. It's easy for it to hold it in, rather than lithium, which is maybe a bigger atom. And that electron can kind of sneak off here or be stolen pretty easily. And when you do that, what they call the effective nuclear charge increases. That's how much positive charge is there pulling on any specific electron. And as you go across, you're increasing that nuclear charge because you're adding protons, and then you're adding electrons, but to that same energy level. If you're adding levels, that would change the whole deal. Also, as you go down the chart, if you take a look at these numbers, as I go down the chart, the numbers are getting smaller. They went 520, 495, 418. They're getting smaller as I go down the periodic table. I'm adding in levels, and it is hard to keep track of that electron on the outside. Pretty easy for somebody to come and take that. So as you go down the chart, the bigger atoms, harder for the nucleus to pull them in, easier for somebody else to take them. So very easy for those electrons to be given up. So on the chart, and you can do this on your periodic table, your own blue one if you want to, But on the chart on here, on the notes, would you mark how the trend goes? And I always mark that to always to the biggest one. So what I would do is I would go up, increases going up, increases going to the right. So smallest, biggest. Okay, so up here, hardest to take them away, easy to take them away down in the lower left-hand corner. Now, there are a few anomalies as you go that, and even when I read those, you might have noticed that. And usually the first one happens when you're going from group 2 to group 3. And take a look at what we're doing. Well, we've filled our, in this example, 3s. And then in the next one, we've got a 3s and a 3p, 3p1. And it's easier for that electron to be taken away. This is kind of a little more stable. So when you have that full S shell, it's a little more stable, a little easy or harder for that electron to be taken away from there. But when you start to put one in the P, those are just a little bit farther away than the S. A little easier to take that away. They have a little more energy, and when they have some energy, you don't have to apply as much energy to get it off of there. Also, if you look at the one down here, you also have an anomaly when you go from a P3, this would be P3, to a P4. That's where another one of those usually occurs. And what happens is when you add that P4, you're putting that second electron in there, and there's a little more what they call electron-electron repulsion. It doesn't take quite as much energy to pull that one out when that first starts. So those are kind of the anomalies that you see in ionization energy. And that is it.